Welcome to Lesson 10 of Puzzles to Exercise the Mind. In this lesson, I'm going to focus on probability, and I'm going to look at some concepts that are a little bit more advanced than what we saw in Lesson number 3. If you haven't reviewed Lesson 3, I'd suggest you do that. I talked about some basic probability in that lesson. This lesson is going to build on that, and I'll talk about conditional probability, the law of total probability, and Bayes' theorem. So it's a little bit more involved in the previous lesson that I focused on probability. Conditional probability is the likelihood of an event occurring given that another event has already occurred. So it's basically modifying the probability of a particular event given some additional information. I have an example of this. So for example, what is the probability of getting a king from a deck of 52 playing cards, but you're given that the card is a royal? So you already know that somebody's drawn a card out and they're saying it's a royal card, but they're not showing you what it is yet. And you're asked to find what's the probability of it being a king. So the information about the card being a royal just limits it to 12 cards. And then out of the 12, there's 4 kings, so the probability is 1/3. And you normally write it this way here: probability of some event given another event has happened. So in other words, like another example might be, what's the probability it's raining given that you know it's cloudy? So that would increase the probability of rain, not knowing whether it's raining or not, but just being told that it's cloudy. So that's the general idea. We have a more technical definition, which I'll get to in a minute. So let's look at the more formal definition of conditional probability. If the event of interest is A and the event B is known or assumed to have occurred, the conditional probability of A given B is written, let me point to it here, probability A given B, and it's defined as follows: the probability of A given B equals the probability of A intersection B, in other words, the probability of A and B happening, divided by the probability of B. So this is a definition. It's not something we can derive. It's actually the definition used in probability theory. So we have an example here. If the probability that it will be raining and cloudy is 0.2, and the probability that it will be cloudy is 0.5, so you would assume it's cloudy more often than it's cloudy and raining. That's why I put these numbers in here, just an estimate for a particular area. What is the probability that it will rain if we know it will be cloudy? So it's the probability, we're being asked the probability it's raining, given that it's cloudy, and then we just use our formula here. The probability that it's raining and cloudy, divided by the probability it's cloudy, that would be our B here. And we're given these two numbers, so we just plug those in, and then we see that when we divide, we get the probability that it's raining, given that it's cloudy, is 0.4. Okay, so that's a simple example. Sometimes it's a bit harder to find some of these numbers here. They're not typically given straightforward as they were in this example. We'll see some more complex examples as we go through this lesson. I have another example here using something called an Euler diagram, which is sort of a Venn diagram for probabilities. So we have this omega, that's sort of our whole probability space, all the different things that could happen in the field of interest that we're looking at. And then we have these different events, A, B1, B2, B3, and then inside the circles are the probabilities that these events are happening. And this 0.34 is basically the probability that neither A nor B2 nor B3 happens. It's sort of the complement of these 3 events. So if you add all these together, you should get 1. So we have a few different examples. I took this out of Wikipedia. I've given the reference here. So the unconditional probability of A is we just need to add up the probabilities inside our circle or our region. So 0.3 plus 0.1, and then just part of B2 is an A, so it's just 0.12. Then we add those three and we get 0.52. Then the probability of A given B1, well, if B1 occurs, then we're sure that A is going to occur because A includes B1, so that's more of a logical deduction here that this is 1. Then the probability of A given B2 is a little bit more complicated because part of B2 is outside of A. So we take using our definition, we take the probability of A and B2, so that's this intersection, that's 0.12, and then we divide by the probability of B2, which is this whole thing here. So that would be these two added together, 0.16, and we divide and we get 0.75. And then the last example here is the probability of A given B3. Well, if B3 happens, it's outside of A, so these are what are called mutually exclusive events. If B3 happens, then A could not happen, so it's 0. And if you switch these around, the probability of B3 given that A happened would also be 0 because, again, these are two mutually exclusive events. I have a few more examples for you concerning conditional probability. This one involves rolling dice. So what is the probability of getting a 2 on either of two dice? So you roll two dice, and you want to know what's the probability that one of them has a 2 on it, given that the different numbers are rolled. So you don't roll 2 1s or 2 2s or 2 3s, and so forth. So here we have our two dice. So we're asking what's the probability of getting at least a 2 here or here, but we're excluding the possibility of getting 2 2s. We're told that doesn't happen. So the number of ways of rolling two different numbers is 6. So say this die could be any one of the numbers, and then the other die has to be a different number. So it's 6 times 5, or 30. The number of ways of getting a 2 on either die is you get a 2 on this one, and then you have 5 possibilities on the other one because we were told your two numbers are the same or not being rolled. Or you could get a 2 on this die and a non-2, 5 other possibilities on this die. So it's 2 times 5, or 10. And so we just divide the 10 by the 30, and we get 1/3. And by the way, I put this exact wording here into a chat GPT, and it got exactly the same answer. It was the same analysis that I've done here. So you may want to give that a try if you're interested in playing around with artificial intelligence. We have another conditional probability problem on this slide. In a certain population, the probability that a woman lives at least 70 years is 0.7, and is 0.55 that she will live at least 80 years. So you would expect the numbers to go down as you increase the age. If a woman is 70 years old now, what is the conditional probability she will survive to 80 years? And we note here that if, in general, if event A is a subset of event B, then the probability of A intersection B is the probability of A. So we'll need that to solve the problem. If you want to give this a try, you may want to pause here because I'm going to show you the solution below on the same slide. Okay, I'm back, and let's take a look at this. So let A be the event she lives. This particular woman lives to 70, and B be the event she lives to 80. So B, sorry to switch the order of this around, but the way I define it here, B is a subset of A. So if she lives to 80, then of course that implies that she live to 70, so that means this event B is a subset of A. And then we'll use our definition of conditional probability. We want the probability of the lady living to 80, given that we know she's lived to 70, so that's probability B given A. And then we just use our formula here. It's the probability, this conditional probability is the probability of A and B given divided by the probability of A, but the probability of living to 70 and the probability of living to 80 is the same as the probability of living to 80. So it's just the probability of B divided by the probability of A. And then we get 0.55 divided by 0.7, and we get 0.733. It's a continued decimal, but roughly 0.73. So it's up a little bit higher than the probability of living to 70, because we already know she's gotten that far, and there's a certain probability of living to 80, so this is the number. And you can use this on various insurance tables that have life expectancies at different ages. So if you're at, say, 65 and you want to know what's the probability of living to 90, you can, and you know the probability of each living to 65 and to 90, you can figure the probability of living to 90 given that you're already 65 using this type of analysis here. So I want to introduce the new concept here, the law of total probability, and we'll do that via an example. We have an art gallery where 25% of the paintings are fakes. When a given collector purchases a painting in general, he has a probability 0.1 of buying a fake for an original. So he's 90% accurate in identifying a fake in a painting that he's interested in. But he never rejects an original as a fake. So if he's interested in a painting and it turns out to be original, he never makes a mistake and thinks it's a fake and then doesn't buy it. So he's 100% in that category. And we're asked, what is the probability the painting he purchases is an original? So we're assuming he buys a painting from this gallery, and we want to know what's the probability that it's an original. So you may want to pause here and work on the problem. It's a bit hard if you haven't seen the law of total probability, and I'll come back in a little bit and then explain the solution. Okay, I'm back. Let's take a look at this. So as usual, we give names to the different events here. So we'll let B be the event the collector buys a painting, and let G be the event the painting of interest to the collector is genuine. And we're being asked, what is the probability the painting he purchased is original? So we want to know the probability that G given B. So in other words, probably he buys, given that he's buying a painting, that it's genuine. But we're given some information here. In general, the probability of a painting being genuine from this gallery is 0.75, since it's 0.5 probability being fake and there's only two possibilities. Then the probability that the collector buys a painting of interest, given that it's genuine, is 1. We're told he never rejects the fake. So if he's interested in it and it is genuine, he's going to go ahead and buy it. So that's how we translate that into a probability statement. And then the opposite of that is if it's not genuine and he's interested in it, he has just a 10% chance of buying it. 90% of the time, he'll even though he likes it, he'll notice that it's a fake and he won't buy it, or perhaps he'll negotiate for a lower price. But that's outside the scope of the problem. So this statement here comes from this. So now we have the information, but we don't know the law of total probability, and I'll show you why we need that here. So from the conditional probability definition, we have this here, and we're looking for a probability of G given B. What's the probability of painting that he purchases is genuine, given that he's bought a painting from this gallery. And we write that out as this here. Now we can apply the law of total probability a second time to this term here, and we write it out this way. So in other words, the probability of B given G is the probability of G and B divided by G, and then we just write it out this way here. The hard part is on the bottom, or at least the part you haven't seen yet is on the bottom, the denominator. The probability of B we weren't given directly, but there's two cases. One is the painting of interest is genuine and he buys it. That's this probability here, again using the law of conditional probability definition, or the probability is a fake and he buys it, and that's this term here. So we've basically broken up the probability of buying the painting into two cases. One it's genuine and one it's not genuine. And we have all the numbers now to plug into this equation. So the top is 0.75 probability of G times this one here, probability of G, probability of B given G, which is 1. So it's 1 times 0.75. And you notice this term here is exactly the same as that. So it's 0.75. And then probability of B given not G is 0.1. The probability of not G is the complement of this. I didn't write it down, but that would be 0.25. And then you just do the division, and you get a roughly 97% chance. Okay, so we'll look at a few more examples of this law of total probability. It can be more than just two possibilities. The idea is you have an event and you break it up over, you intersect it with all the other possible events that make up the entire probability space. I have a nice picture of it in the next slide. I'll show you what I mean there. Law of total probability is stated more generally on this slide. We have a collection of mutually exclusive and collectively exhaustive events, this B sub n. They can either be finite or countably infinite. Mutually exclusive means that if one of these B sub n's occurs, say B sub 3, then none of the other ones can occur. And the exhaustive means that all the possibilities in our probability space of interest are covered by one of these events. So for the previous problem, we only had two of these B's. We had the event that the painting was genuine or that it was not genuine. If you recall, we broke it into two possibilities. But you can do it more generally as we have here. And then the probability of A is just the intersection, the probability of the sum of the probabilities of the intersection of A with each one of these B sub n's. And each one of these could be rewritten using the definition of conditional probability is this here. So normally you would either use this form of the law of total probability or this form, depending on how the information is given to you. And I have it drawn pictorially here. You have an event A, and if you don't know what A is, but you do know what the probability of A is intersected with B2 and B3 and B4 and B5, then you can just add those up and get the probability of A. That's why it's called the law of total probability. You're kind of breaking it up into pieces using some set of events that in total equals the entire space, which is represented by this this rectangle here. And you notice the probability of A intersected with B1 would be 0, and the same for B6, but that's fine as long as you have your entire space covered and you can determine these probabilities of A intersection with B2, B3, B4, and B5, you're good. And as I say, for the example we had in the previous slide, we just had two events. We had G, the probability the painting was genuine and the probability the painting was not genuine. And B was, or our event A here was probability of buying the painting from the particular art gallery. Well, I have a few more examples that help fortify our understanding of this principle here. I have an example here that'll require the law of probability to solve it. We have 3 bins, each with 100 marbles in the bin. And bin 1 contains 75 red and 25 blue marbles. Bin 2 has 60 red and 40 blue marbles. And bin 3 has 45 red and 55 blue marbles. You randomly select one of the bins and then randomly select a marble from the selected bin. How likely is it that the selected marble is red? So I'm giving you a big clue here. It's the law of total probability that we need to use to solve this. I'll pause for a second here and then I'll come back and give you the solution. Okay, so let's look at the answer. The first thing is just to write down the probabilities here. So if we picked bin 1, then the probability of red, since there's 75 out of 100, it would be 0.75. And for bin 2, the probability of red would be 0.6, since there's 60 out of 100. And then similarly for bin 3, the probability, if you've picked this bin, the probability of getting a red is 0.45. And then we can use the law of total probability. We're interested in the probability of selecting a red. And the 3 bins, B1, B2, and B3, notice I used the same notation as we did in the definition of the law of total probability, just to make it easier to map things in your mind. But basically they're mutually exclusive, and they fill out the entire space of possibilities. In other words, you have to pick one of the 3 bins, so they're exhaustive in that sense. And so you just write out the equation with our red being the thing of interest, and then we can plug in, since we have all the numbers here, we have the probability of red, given that you've selected bin 1, that's 0.75, and we're assuming that the bins, since the bins are selected randomly, that the probability of B1, B2, and B3 is 1/3 each. I mean, we could have changed it. We could have said you had a 50% chance of picking bin 1 and 25 of bin 2 and bin 3. And then we would have just plugged in different numbers here. So once you identify that this is a law of total probability problem, and then you extract the information, it's pretty easy to just put everything into the equation that we have here. So the answer is 0.6 in this case. I have another example here for you to consider. A small and dangerous park has 3 sections with different concentrations of poisonous plants. So maybe somebody was experimenting with different plants, and they later gave up on it and gave the area away as a park to the local municipality. And so the park has been divided into 3 sections, A, B, and C, and it still has these plants that are poisonous to eat. Section A is 50% of the park, Section B is 30% of the park, and Section C is 20%. And the percentage of poisonous plants varies based on the section. Section A has 20% poisonous plants, Section B has 40% poisonous plants, and Section C has 70% poisonous plants. And you pick a plant from one of these sections with probability 50% from A, 30% from B, and 20% from C. So I don't want to say randomly, but just based on the size of the section, you pick a plant from that section with a given probability. And you want to know what is the probability that the plant that you've picked is poisonous. So I'll pause here, or you may want to pause here, and then I'll come back and give you the solution on this slide. Okay, I'm back, and we'll let P equal the event that you've picked the poisonous plant, and then we'll do the law of total probability based on these mutually exclusive and exhaustive events A, B, and C. They take up all the possibilities of where you could have selected the plant from. So here's the law of total probability, and we have all the numbers we need. The probability that you've picked the plant from A, given it's the biggest area, is 0.5, and we're told that 20% of the plants from there are poisonous. And then the same thing for B, that's the next biggest area, so the probability of picking from there is 0.3, and the probability of the plant from there is poisonous is 0.4. We do the same for C, given the information we're given, and we just multiply these three terms out and add them, and we get a 36% chance that the plant that we've selected is poisonous. We have another concept here that we saw before in the example was the art gallery, and I'll kind of work through it here in more detail. So it's known as Bayes' theorem. This is very current, that even though it was discovered quite a long time ago, it's very current in terms of research and usage in the people working in probability. In fact, there's entire books on Bayes' theory. This is just the tip of the iceberg here, the basic form of the theorem. So from the definition of conditional probability, we have the probability of A given B is defined actually by this formula here, which we saw before. And of course, B can't be 0, so just make that clear here. I probably should have emphasized that earlier. So B is not 0. And then we can just flip this around. The probability of B given A, the top looks the same, right? The order of, when you intersect A and B, the order doesn't matter. So this is the same. But then in the denominator, it's A instead of B. So you have these two equations by definition. And if we solve for the probability of A intersection B here, then it would be probability of A times the probability of B given A, and then substitute that into equation 1, we get basically Bayes' theorem. So we have our equation 1, we solve for probability A intersection B here, and we put that in the numerator. And under the assumption the probability of B doesn't equal 0. So if you recall, we did that with the art gallery example, and then I went ahead and I also had to expand the denominator there. And that's quite common when you're using Bayes' theorem, that you first start with this here, and then in a lot of cases you need to use the law of total probability to find the probability of B. And as I say, this is quite extensively used in modern day probability and statistics. The three prisoners problem makes use of the law of total probability and also Bayes' theorem, or at least the solution of the problem does. It's also part of a collection of similar problems that have almost the same solution. This is one of the more popular versions. There's another version called the Monty Hall problem, which I'll explain a little bit later on. So we have three prisoners, A, B, and C, in separate cells and sentenced to death. The governor has selected one of them at random to be pardoned, and the warden knows which one is to be pardoned but is not allowed to tell. So prisoner A gets very anxious, and he knows the warden's not going to say who's going to be pardoned, but he tries to get some information out of the warden, and he asks makes this following request here in quotes. So prisoner A says, if B is to be pardoned, give me C's name. In other words, let me know that C is going to be executed. If C is to be pardoned, give me B's name, in other words, letting A know that B is going to be executed. And if I'm going to be pardoned, in other words, if prisoner A is going to be pardoned, then secretly flip a coin to decide whether to tell me it's B or C who's going to be executed. So that's the request from A. And surprisingly, the warden decides to go along with A's request, and he or she, I don't know if male or female, but let's say the warden gives prisoner A B's name. In other words, the warden tells prisoner A that B is going to be executed. So at this point, A is pleased because he believes that his probability of surviving has gone up from 1/3 to 1/2. His reasoning is that there's just two of us left now, and I know B is going to be executed, so it's either me or C who's going to get pardoned. So I have now a 1/2 probability. And A secretly tells C the news, and C, who reasons differently, he says that he tells A that, well, your chance of getting pardon is still just 1/3. Nothing has changed for you, but in my case, my probability of getting pardoned is now 2/3. So the puzzle is, well, who's correct? Is it A or C in terms of their analysis of the situation? Let's look at a solution to the three prisoners problem. We'll let A, B, and C be the events that the corresponding prisoner will be pardoned, and small b, lowercase b, be the event that the warden tells A that prisoner B is to be executed. And we know that to be the case. That's actually happened based on what was said in the statement of the puzzle. And what we're looking for is, what's the probability that A is pardoned given the event small b, that he's been told that A has been told that prisoner B is to be executed. I've copied the request from A to the warden down here from the previous slides because we'll need to refer to that. And the other thing I should have mentioned is, well, actually two things I should have mentioned. One, we assume the warden is telling the truth. So what he said to A about B being executed is, we assume that to be 100%. That's correct. And also before before this process, and we assume that the governor has an equal probability of pardoning A, B, and C. We could have done the problem if the probabilities were different. If for some reason the governor liked A and there was a probability 1/2 there, but we weren't given that. So we're just going to assume that the probability of these pardons of A, B, and C is 1/3. Okay, so we have that information, and we're looking for the probability of A given small b. Using Bayes' rule, we have this here. You notice when you use Bayes' rule, the order of the condition gets switched, and then you just have the probability of A here and the probability of this condition divided into it. So that's the Bayes' rule. Then I've just copied the numerator here. And the bottom, we don't know the probability of this, but we can break it up into three different events which are mutually exclusive. Either A is being pardoned and the warden gives the information that A related to the small b, or B is being pardoned or C is being pardoned. So there's three mutually exclusive events, and we can use the law of total probability to write that out here. All right, so the only question is to fill in these three things here. The top one is, we know the probability of A being pardoned is 1/3. That was the assumption we made. And then what's the probability if A is being pardoned that the warden says B is going to be executed? Well, we have that in the request from A. A says, if I am to be pardoned, secretly flip a coin to decide whether to give me the name of B or C. So this would be 1/2 because of the coin flip statement here. then you notice this here and this here are the same. So we'll just copy that down. Then the next two are a little bit tricky. The probability of B is 1/3 again, and the same for probability of C. But the probability that a B is to be pardoned and the warden says B is to be executed, that's what this little b means. Well, that probability is 0 because we assume the warden is not lying, he's going to tell the truth. So this is 0. And then we have the last one to look at. What's the probability that C is to be pardoned and the warden tells A that B is to be executed? So if C is to be pardoned, the warden agreed to give A B's name. So that's 100%. That's what's going to happen in this case here. So that's just the 1. And if you do the calculation here, you get 1/3. So A was incorrect in his logic, and prisoner C was correct in saying that the probability that A would be executed or pardoned, is no different after this new information from the warden. But by implication, the probability that C gets pardoned is 1 minus 1/3 now, which is 2/3. So actually C's probability of getting pardoned went up quite a bit. So this is quite counterintuitive. I'll try to give you some additional explanations on the next couple of slides, and that may help a little. Let's look at the problem from another perspective. First off, prisoner A did not gain any information about his fate from the response from the warden, because the warden, he already knew in advance the warden was going to tell him B or C. The way the question was posed to the warden, he would never reveal if A was going to be pardoned or not, or executed or not. He's not giving A any information. So maybe another way to look at it is if the warden agreed to something different, if A said, flip a coin and tell me whether or not B or C is going to be pardoned or executed, and let me know based on the coin flip. So let's say if it comes up heads, and that means the warden needs to tell him what's going to happen to B. That would give you a different probability because it's done randomly. This isn't done randomly. The warden answers the question to A in such a way that he doesn't give any direct information about the outcome for A. So looking at it a little bit further, since the warden says B will be executed, it's because of one or two reasons. And we'll see that the chances here are for pardon are twice that for C compared to A. So in one case, the warden will give this answer that B will be executed because C is going to be pardoned, and that's a 1/3 chance of that happening. On the other hand, if A is going to be pardoned, which is 1/3 chance, and the coin to decide whether to name B or C to be who's going to be executed is 1/2. So overall, there's a 1/2 times 1/3, 1/6 chance B was named because A will be pardoned. So you can see here that the probability of C getting pardoned is twice that of A, given this information here. So that kind of confirms the analysis from C. Now you may ask, well, why doesn't the 1/3 and 1/6 here add up to 1? That's because this is only 1/2 of what could have happened. The other thing could have been that the warden would have said C is to be executed, and then you would have these two possibilities, except you'd have a B here instead of C, and you still have 1/3 and 1/6. So either way, A's chances are of being pardoned are half that of the other person who's named here by other than the other person named by the warden, I should say. So if he says B, then C would have twice the probability of being pardoned than A, and if he said C, then B would have had twice the probability of being pardoned than A. So that's another perspective. Hopefully I haven't confused you. I'm realizing now as going through this might be a bit harder to understand than the kind of the automatic or manual solution we did on the last slide, where you just plug things into the equation. But uh, give it some thought. This is another perspective on the problem. I have one more perspective on the next slide, which I'll describe. So let's try one more way of looking at this. Prisoner A has a 1/3 chance of pardon either before and also after the response from the warden. Knowing whether B or C will be executed doesn't change because the warden is going to give the answer B or C in any event. That's 100% A knows that that's what he's going to be told, and the warden intentionally avoids giving A the information about who is going to get pardoned. Look at it this way. If you have A, B, and C here, and let's say B is going to get pardoned, the warden does not randomly pick between B and C to tell A the information about the outcome of B or C. He doesn't flip a coin and it comes up B and he says, all right, well, B is going to be pardoned, and he tells A that. That A knows 100% that he is going to get executed. That's not what happens. What happens is the warden sees that B is going to get pardoned, and he avoids giving A an information on B, and he tells A that C is going to be executed, and that doesn't change A's information because A knows either way he's going to be told B or C, and it's not going to be the information that allows A to conclude what's going to happen to him. So, assuming A and C both understand this, A and C realize that if A is not going to get pardoned, then the remainder of the probability, the 2/3, is going to go to C. So C would have a 2/3 chance of getting pardoned. Okay, so that was my best attempt, 3 different ways. Perhaps the first way is the least difficult to understand, but it gives you the least amount of intuition also. And there have been simulations of this game, and the numbers that we've computed, in fact, do come out when the simulations are run. So we have an exercise for you to look at. The probability that we did several slides back using Bayes' theorem and the law of total probability, we could compute the same probability for C, given that we know that B is going to be executed. So it follows very similar steps that what we used before, but you may want to use that to practice Bayes' theorem and the law of total probability. Then I have some references here. There's a Wikipedia article on the 3 prisoners problem. Then this is equivalent to something called the Monty Hall problem, which is probably this puzzle is better known as the Monty Hall problem, to be honest. And I have a couple of references for you here on the Monty Hall problem, and then there's also a Wikipedia article on the Monty Hall problem. So I'll just give it to you very quickly. The Monty Hall problem was from a game show, and the contestant was shown 3 doors, couldn't see what was behind them, and one door had a car, and the other 2 doors had something undesirable. They typically say a goat, but from watching the show many years ago, I remember it wasn't always a goat, but it was something you didn't want. So the contestant gets to pick one of the doors, and he or she is not shown what's behind that door. So he picked the door number 1, and then the game host shows you what's behind one of the other 2 doors. Now the game host knows where the car is, of course. So when he shows you the other 2, opens one of the other 2 doors, he's going to always show you a bad prize, which gives you the impression that, well, now there's only 2 left, and I have maybe a 50% chance. So the game host says, do you want to switch or keep your present the door that you've picked? And the correct answer is to switch, because of the analysis we've done before. There's a 2/3 chance that the other door is the door that has the car, and only a 1/3 chance the door that you picked initially has the car behind it. So it's very similar to um, the three prisoners problem. And as I say, you may want to take a look at these two videos here. They kind of look at different aspects of the problem and give different explanations. But it's rather fascinating because people played this game show for many years, and no one really realized that it made sense to switch until the game was analyzed by I guess some mathematicians. We have another concept here called expected value, which I'm going to use in the puzzle that follows. But let's take a simple example first. So you're planning to bet $100 on a particular outcome of a sporting event, so for example, a football game. And as I record this, today is the Super Bowl in the United States. So if your gamble is wrong, you will lose $100. If you select the correct outcome, you will win 500. And based on your estimation, you have an 80% probability of losing, so not too good, and a 20% probability of winning. So should you make the bet, or should you, or at least what's some input that would help you make the bet? So if the payout was the same, of course you wouldn't want to do the bet because you've kind of reasoned that you have an 80% chance of losing. But as you get more money for betting on a long shot, you may want to analyze to see what's the relative payoffs. That's something called expected value. It's sort of a weighted average, and you just take the 0.8% probability of losing times your $100, and then you add to it the 20% probability of winning times the $500, and you compute these two numbers and add them, and you get an outcome of 20. So at least from the expected value, I realize you're only going to do this bet once, but if you did this type of bet many, many times over and over again, like in a simulation, then you would stand to make money. You would on average make $20 per bet. So if you ran the simulation 1,000 times, you would roughly make $20,000. So this is kind of an analysis you would use, at least give you some sense. Now, if this came out negative, you may want to reconsider betting on your favorite team and either switch to the other team, or maybe not bet at all. But this is something that's commonly used in probability and statistical analyses. So we have another problem here that makes use of Bayes' rule and the law of total probability. An expert on precious metals is offered a rock which potentially has rhodium. I looked this up. It's actually the most expensive precious metal per weight, even more so than platinum or gold. The owner of the rock will sell it for $2,000. If the rock contains rhodium, and we don't know that for sure when the rock's being sold, it'll be worth about $10,000. And the expert knows that. So the expert knows also knows that the rock comes from a site where 1% of the rocks that kind of look like this rock contain rhodium. And further, the expert has a detection device which indicates whether a given rock contains rhodium. Now, there's certain limits to this detection device. The detection device will always detect rhodium if present. So it's 100% accurate. If there's some rhodium in that rock, it'll show positive for rhodium. But it's only 90% accurate if no rhodium is present. So that means you have the rock like this one here, and it's trying to be sold to the expert. In 10% of the time, it'll give a false positive. In other words, there'll be no rhodium in the rock, and yet it'll show it as having rhodium 10% of the time. And 90% of the time, it'll say, no, this is not a good rock. It doesn't have the precious metal we're looking for. So in addition, you can only tell for sure whether the rock has this rhodium in it when it's melted down. But the owner of the rock, the prospector who wants to sell it, is not going to let you do that. So you have to basically decide to take the gamble or not. To pay $2,000 with the potential of making $10,000, or if it doesn't have rhodium, then you're basically getting a useless rock for $2,000. So the question is, should you buy the rock, or at least what is the expected values, to give you some idea of whether these relative values and percentages make sense in terms of the expected value. So let's solve the problem. We'll let A be the event that a rock from the site contains rhodium, and we were told that the probability there was just 1%, and we should say maybe the rock that kind of looks like the rock that the prospector is selling. So there's only a 1% chance that that rock is going to have rhodium. And then let B be the event the detector indicates the presence of rhodium. And we know that the detector has certain limits to it, which we'll describe down here in the terms of the probabilities. So what we want to know is, given that the detector indicates the presence of rhodium, in other words, B, what's the probability that the rock actually does contain rhodium? So we want the probability of A given B. And then we'll work out an expected value based on this calculation here. So the probability of B given A is 1, right? That was the thing about the detector being 100% accurate. If a rock actually does contain rhodium, it always gives you the positive result. So that's 1. If the rock doesn't have rhodium, this probability I'm pointing to down here, then the detector 10% of the time will say it does. So it's not 100. It's not. I mean, it's pretty good, but it's still going to get a false positive 10% of the time. And then if the rock doesn't have rhodium, 90% of the time, it'll tell you that. So it'll give you a correct true positive, true negative, I guess you would call this, right? It's true and it's negative in the sense that it doesn't have the rhodium in it. The probability of A, which I already mentioned here, the probability that a rock that looks like the one that's attempting to be sold is that has rhodium is 1%, and the probability it doesn't, of course, is the 1 minus that, so 0.99. So we can use these numbers in doing a calculation for this probability we seek here, probability A given B. And we'll do that on the next slide. So I've copied the probabilities that we wrote down from the previous slide up here. We'll need to use those. So first we're going to use the probability, law of total probability, to find the probability of B, and then we'll plug that into the Bayes rule down here. So the probability of B, and again I wrote it back down here on the bottom just to remind us. So B is the event the detector indicates the presence of rhodium. So either the rock has rhodium or it doesn't. Those are the two cases. So this is the probability that the rock does have rhodium in it and it's detected. And this is the probability the rock doesn't have rhodium in it and yet you get a false positive. So this probability B given A is 1. We computed that. And the probability of rock of this type from this site has rhodium is pretty small, 0.01. And then the probability of B not A, we computed that to be 0.1. And then this is the probability that a rock from this site does not have rhodium, and that's pretty high. It's 99%. So you just add, multiply, and then add these up. You get 0.109, excuse me, and now we can apply Bayes' rule. We're looking for the probability that the rock contains rhodium, given that the detector indicates it does. So that's this, and then we just use Bayes' rule here. That's the formula for it. And we've computed where we know what B given A is, that's 1. Probability of A is pretty small, 0.01, and then we divide by B, which we computed up here. And so we get 0.0917, so a little bit over 9% probability of A given B. And so the probability of not A given B is 1 minus this here, so it's 0.9083 or approximately. And then we can do an expected value just to get a sense of whether or not the purchase makes sense. So we have the minus $2,000, so if you guess wrong, and that would happen, in other words, the rock doesn't have, even though the detector says it has rhodium, the rock doesn't, that would be probability 0.9083. And then the probability the rock actually does have rhodium, and you would get your you would make $10,000 by reselling it perhaps. So if you add these two together, the expected value is minus almost $900. So here's a good example of where clearly you wouldn't do it if it was just a one-time deal, and if it was like the same prospector, every day or several rocks a day, he tried to make the same deal with you, you would be losing, 100 or 1,000 times this if you kept making the same bad deal with the prospector. So given this expected value, one, you would turn down the deal, and then two, you might tell the prospector, given these probabilities, we need to make this, become positive. I mean, you may not show them the calculations, but you might say, I'll give you $1,000 for that, and that would change the, that would offset the negative here. Maybe you would only give them $750. So you have to lower this purchase price in order to get this to become positive, and in order to make the deal make sense over time, where you would, buy the rock from this prospector over and over again. Or of course, it would be different rocks, but so some information, in terms of the what the expert would be looking for in order to make a decision, and that's the last puzzle from this lesson. I will put the references, which there's quite a few here. I'll put them in the information to this video, so you don't need to copy down the links. You can just click on them from the information underneath the video.